complete. Okay. Okay, so hello everyone. Thanks again for being here another Friday. Today we will start the second day regarding RH radiative transfer code tutorial. Today the description that I will put in the slide is very simple. So we will focus on the atoms.input and the atom itself, given atom. And how to configure it for making or for synthesizing a spectral line. And we will cover how is an atom created in RH, or what are the items that we have inside an atom, and which items we can change and which ones we just need to understand what they mean. Okay, so then this is very simple. I will try to have the editor split it in two today. I hope it's easy to follow. And also I will change the color. So last week it was a black background or with colors on top, and now I'm using white. So if you prefer one or the other, just let me know today or other day. But I believe that it may be easier to see the characters and the fonts with a white background. So let's see. Okay, so then the idea is we are going to be in a folder that is inside the RH distribution, again, RHF1D, and it's a folder that is called atom config 1. So today we will cover number 1, and then next week it will be number 2, where we check or study different configurations are also related with the atom or the transition. So let's go through the script. The idea is that, again, we will focus on computing in non-LT the calcium infrared transition, so 8542. And in order to define the different parameters for this computation, we can go to the atom. So if you remember, we defined this atom as an active last week, so then it will be used for computing the population. So if we open this atom, this is this one that we have here. So you have different information. And the first thing is that this symbol, it marks a comment. So it's just something that you can add. Then you have the atomic species. So the idea is that the atoms are ready in general, but I think it's good to know some of the things that are there. And some things you should change when you are doing the computation. So in general, the first part, we should not change it. There's some general information like the number of levels, the number of transitions that we have between those levels. Then we have the information specific of each level. So the energies in centimeters up to -1, then the G values, then the spectroscopic information, the ionization state. So it's starting 0 for non-ionized, and then this is calcium 2. So they are all these levels are 1. And then we have the ionization, the calcium 3 ground level. And then a label that is used for designing that is assigned to this level. So it means that the transitions that comes here, they indicate which levels produce the transition of interest. So, so then, as I said, this information should not be changed. And in general, if you want, you can check for example, with NIST, that we can go there later, and check that everything is in the NIST and the numbers are updated. So then this is more or less what I say in the beginning. And then what I said is that when we enter in the transitions itself, that is this part here, is where we can and we should change things based on our research interest. So the first part, this J and I are the upper and the lower level. So just a transition between two levels is a spectral line. There are some comments that designate that these two transitions are H and K. And then these other three transitions are the infrared triplet. So for example, in this case, it's also stated that this will be 8542. So then it's saying that the transition between 4 and 2, these two levels, 4 and 2, it will be the one producing 8542. I think you should not do it every time, but if you are going to work with an atom a lot, it's good to double check that, so you can go to the NIST. And if you look for the calcium 2 transitions between 850 and 855, you will have this one, and it's telling you that is between 13,000 and 25,000, these two levels. And if we go back, so you can see that the 13,710 and the other one are at the same levels. Also, you have the F value here. That is, this one again should not be changed. And then you can also check in NIST, if you ask to provide the F value. Just let me go back. So we said, I want to know about calcium 2. I want to know about these wavelength regions. Then you click in advanced settings, and then down you can ask for the log GF, for the F value, and for the G value here. So then those values, you can see that the G is 6 and 4. If you go back, you will see that this 6 is the lower level and 4 the other one. So this information is in the NIST. And then it says that this 7.24 up to the -2, the F value, and then you can see that the F value here is that one. Okay. And then in fact you can compute the log GF for the transition as defined in the atom. So then in order to do that, you just multiply this F by the G of the lower level. In this case is 6. So then 6 times this F and the logarithm of that is the log GF of the transition. So then you can check if this value is reasonable and is similar to the one you have, for example, from NIST or from other database. Okay, because this is the one that we will use when solving the radiative transfer equation. Okay, so then these three values, they should not be changed because they are from the database. And then from here on, we can change these different parameters. So let's start with the first one. I wrote here a description. The idea is that we will check in the next class the difference between complete redistribution and partial redistribution. In the case of calcium infrared, the lines in general work well under the complete redistribution. So then you just need to have here the command void, and then it will assume complete redistribution. But if you change this and you put PRD, then the code will compute that transition in particular, assuming partial redistribution. So for today, we just leave it like that. We are going to focus only on this line. But for next week, we will play with the calcium H and K lines, and we will change this from void to PRD and study the difference. Okay, but basically only two options, either void or PRD. Okay, then the next item is n lambda, that is this one. And this is the number of the total number of spectral points that you want to have for a given transition. So then, for example, in this case, we are saying 50 for this calcium H line, or okay, and then 70 for the calcium infrared. Okay. Then the next one is called symmetry, and in this case, it's a new thing compared, for example, with SER. And the idea is that you can choose either with A, so that they is asymmetric or symmetric. And if you don't have the A, then the code will solve just half the profile, and it will assume that it's symmetric. This in general, it's not good for a transition that you are studying for the profile itself, because you can have gradients that make the profile not symmetric, but is usually enough for obtaining the populations of a given transition, or of the levels of a given transition. While if you are interested in a given line, then you should always have a sim, so A with an A. So the reason is, if you see, for example, the transition of calcium 8542, it's from level 4 to 2, but you also see that there are transitions where level 4 is involved, like this one or this one. So then it's important that you solve or you compute the populations of a given level with high accuracy. So then even if you are not solving the profile itself for these different transitions, it's important to have them properly computed, because they affect to the populations that define the transition of interest. Okay, so what we are just doing here is trying to speed up the computation, removing things that are not necessarily important. So if you're not going to analyze this spectral line at all, then you just need to have a reference of how it impacts on the population. Okay. Then we start on another part that is also related with optimizing the computation of the non-LT problem. So we have Q-core and Q-win. So they define two regimes where the code distributes the spectral points in a different way. So in the case of Q-core, is an interval, a wavelength range, where the spectral points are distributed linearly. And then in the case of Q-win, it's a region outside that one, where instead of having points linearly distributed, the points are exponentially distributed. So you can cover a wider wavelength range, but without using too many points. And the reason is, again, the behavior or the property of non-LTE, and is that given a spectral line is in general sensitive to the non-LTE problem, mainly in the core. So then it's important to cover the core with a dense grid. But then as you move to the wings, things are in general very smooth. So then having a high sampling in the wings is in general not necessary, and it's time consuming. So then RH is offering you the option of defining where you want to have a dense grid and where you want to have a coarse grid. So we will check that in detail today, but it's just to have an idea of how this works. And for example, in this case, just let's check what this Q-core and Q-win means. So they are, so you see here a value like 5 and 150. They are in Doppler units. So in order to understand what they mean, we can put the values that we have here. So we have that lambda 0 is this one that is defined here. Then we need to go to the keyword.input. Okay, let me bring it here. As I said, we will go through all the items in detail in the future, but the important one is that almost at the end, we have this part that says that it's a typical value of microturbulence. That is, I think here it has a different meaning of the usual one, and is used for converting the Doppler units that we have in the atom, so these ones, to wavelengths. So then usually this is defined like 3. You can change it, but it's only going to change how the final translation of these points to wavelength is done. So in general, we don't change it, we just keep at 3. It's in kilometers, but we usually have 3, but of course you can change it. So then this value in meters per second is 3 up to 3000. Then we have the speed of light also in meters per second. And then in this case, we are saying that Q-win is 150 and then Q-core is 5. Okay, so then the spectral range that is covered by Q-core is defined like this. So it's this characteristic velocity that we have in the keyword.input divided by the speed of light, and then multiplied by Q-core and the wavelength. now I'm going to do a print. And the same for the win. So it's the same factor here, just adding Q win instead of Q core. So then let's do this. So then it's saying that the code is going to use a dense grid. I multiply by 10 and I change, this is in Amsterdam. So it's going to cover the core in plus minus 0.4 Amsterdam with a dense grid. And then it will, from that point on until almost 13 Amsterdam, it will be a grid that is exponentially distributed. So the points are coarser. And the idea is that this will give you, in general, as we will see later, basically the same profile, but saving a lot of time than when if you have a linear spectral sampling from the core to the far wings. Okay. Han, do you want to say something?
Yeah, I think no, that's a good
okay.
explanation of what happened. I just want to make sure that it looks a little bit contrived to do it this way, to specify these distances in Doppler units, but that is the more natural unit in terms of what happens within the line. So if you would specify it directly in nanometers or angstrom, you have no idea exactly what you are doing in the line in terms of physics. And so that's why this is a little bit of contrived, where you first specify it in Doppler units, and then use this V micro characteristic to convert to wavelength units. And then, of course, inside the code, it has to be converted at each location back to Doppler units to calculate the voice functions for it. So and the whole reason that this is done carefully is that you want to have as best an estimate of the radiative rates in each transition, so that you can estimate the population numbers as best as you can. So that's why this goes a little bit in length to specify all these things carefully.
Yes. And I think I would say that it's fine, because as we will see later, it's relatively easy to check what are the numbers. Even if you don't use this formula for computing the exact wavelength, we just do a computation and we plot the profile, and you will see what are reasonable numbers. And then you just keep that for all the computation. You need to change it again.
Yeah, and in addition, this V micro characteristic in the keyboard.input file is a way to change the width of your all the lines at the same time. It's just one edit, so you can play with that a little bit, and it changes every line. While in the atoms.input file, you have to specify each line individually.
Yes.
One more thing about the void.
Yes.
So there's an additional option, or two additional options. One is not very well documented, but there's one that you can put Gauss there, also in capital. So it will just use a Gauss profile. Yes, exactly. And you can also use composite there, and then specify components. For instance, if you have isotope splitting, you could use that in that way, but that's a kind of a hidden option. To make people aware that if they're ever interested in, they can contact me and I'll explain that.
I also have an example, so I can share it.
Okay, good. Sorry.
Yes. Not today, but if you want, I can add it for one of the
that would be
okay. Okay, just let me take note.
Yeah.
Okay, so then let's go back to So just this is a reference. At the end, in my case, for example, I always work with numbers here. Later, we will check how you can get the intuition to know more or less which numbers you need to use. But before that, let's go to this van der Waals approximation. In this case, you can have two options, or just un sol, like is in now, or you can type Barclay if you want them to be computed, assuming the Ansty, O'Mara, and Barclay theory. One warning, though, is that the tables that they were published for the theory only works for neutrons. So in general, you cannot use them for single ionized or high ionized atoms. So in this case, if you just you put Barclay there, the code will say that it cannot treat the lines, assuming this theory. It is true that later on, I think Barclay 1998, they specifically computed for magnesium 2, barium 2, and calcium 2, the broadenings due to collisions. And those are included in this side. So in the case of this side, it will be included, the correction. But in RH, this version, it doesn't include it. It's something that we may add in the future. But in the case of this side, we're just taking those values manually and inserting. But for this class or tutorial, we will always work with unsolved approximation when using single ionized transitions, atoms. Okay, so then I think this is the final comment before starting the example. And yes, here I added an additional comment. So yes, so what I was trying to say before, in the case of SER, and we will do the same in this side, also in this side is a bit different. But in the case of SER, you had in the wave-grid file, you said like iron 1.5 micron. So then you have one line there. And this is the only line, it's solved, and it's NLT. In the case of RH, even if you are interested only on 8542, you are going to solve all the transitions that are included in the atom. So then this is an advantage because you gain lines that you don't need to specifically define or just get them by free. But at the same time, it means that also they need to be properly defined in order to really have a good estimation of their impact on the levels that define the transition of interest. So what I mean is that the number of points that you have for the other transition should be relatively generous. So you cannot put here like 1, because then the calcium age, that is a transition that is important for populating the other levels, will be not properly solved. So you have to have some numbers. I cannot tell you which is the best value, but in general, 1 or 10 is probably too small. So you need to have more points in order to have properly covered the transition, even if it's not the one that you are going to analyze. So in general, atoms, they have a reference or a baseline, but just think about that. So when you solve in non-LT a transition, you are solving a full atom, and then there are other transitions that affect your transition of interest. And this is very different from NT.
So Carlos, one more comment. So in this case, I think for the calcium H and K lines, it is actually important to have there also asym because they overlap. Yes. So you have to be careful there as well. Yes. Right. So to clarify, when there are no velocities, you can the both sides of the line are exactly the same as long as the continuum intensity or the continuum opacity is flat, right? Yes. So that's why you actually get a slightly better wavelength distribution if you just calculate half the profile and then just copy that calculation to the other side to calculate the radiative rates by integrating over the line. So that's why there it's actually something that was taken over from how it was in multi, but in multi you didn't have overlapping lines, so you didn't have to worry about this. Okay. But in the case of calcium H and K and certainly magnesium H and K, they are close enough together that in this case you would want to use asym so that you take into account the overlap of the lines. Okay. Thank you. Yeah. Okay. So then. Just again, as a summary, just try to understand the differences. So now
you don't have one specific line that is isolated from everything. It's connected to other transitions in the atom. So it's important that those transitions are relatively well described in terms of number of points, and also, as Han mentioned, in terms of asymmetry as well. Okay, so then I'm going to start some tests. Is there any questions so far? Because I think it's a bit technical, but I hope that with the next test, we will understand it better. But I think Dato already has a question, so please.
Yes.
Yes.
Yeah. So if we have some atmospheric model with constant velocity field and maybe constant magnetic field, does it still matter to have that asymmetric flag in the atom file?
I think no. I think if everything is constant, I think
no. There is a little bit of a warning though. When you have no velocities, normally the code uses the Fourier solver. When you put velocities, even if they are constant with height, and so it wouldn't make, and it would still make sense to just calculate and shift. The code uses a different solver, so you actually will get slightly different just because of the numerical accuracy of different formal solvers.
Yes.
So it's something that happens behind the screens, if you will, but that is
behind the curtain.
slightly. So yes, with constant velocities you could use. I think I may be proven wrong, but
yes.
I think it is safer to use sim as well, because computers are fast enough now.
Yes.
This really came from a period where every wavelength point counted. Nowadays you don't. It doesn't really matter. So so I would use asim by default in most cases, because it's just a hassle to have half-line profiles in most of the time, and you don't gain much.
Yes.
I see. Thank you.
Yep. Yep. Okay. So then what I'm going to do now is just change the atomic configuration, run the RH, and then so this is like previous week. So I run RH, I just call solve ray, and I compute the profile of mu equal 1. Then I read everything, and then I just take the information from ray and the spectrum. So the idea is that I will do this multiple times, changing the atom configuration in order to compare different cases. I did it already, so I'm just having everything commented, but I will show you the figures that I generate. So then in the first case, we are going to compare two configurations. So then what we do is, just for understanding more or less how lambda and lambda works, we have that everything is the same, but we change in one case n lambda to 10, and in the second case n lambda to 100. Okay, so I run it once. I had a stop here, example, and then I saved the file, and then I change the atom, and then I run it again, and then I save the file. Okay, and then after that I restore the two save files, and then I make this plot. Okay, so then let's check this plot that is already in the Dropbox folder. So case 1 is a computation with 10 wavelength points, and case 2 is with 100 wavelength points. So then you can see that the orange line, it has 1, 2, 3, then 4, 5, and then basically the line, it's just not good. And then in the case of the blue line that has 100 points, you can see that the line is smooth, and it has a typical behavior of the calcium infrared that is very steep here, and then a change in this part that people call the knee of the line, and then it's smooth in this direction. So then this is just a very, very simple example where you see that having not enough points will make artifacts or a profile that is not realistic, like this one, where things are not smooth. So then, yeah, so this is just as a reference. And then what I say here is that there's no strict rule, but I would say that in general, you should aim to have between 50 and 100 points, spectral points in total. You can add more. Yeah, I think it will reduce a bit the computational time, but just always check if you need. So if you put 1000, you probably don't need them, but between 50, 70 or 100 is probably all the values are fine as soon as you increase them. Okay, so then this was an example of this value. Now the next one, so let's check how QWin or Q-core works. So then in this case, is case 3. What I'm going to keep fixed is n lambda 40, because you will see that it's easy to visualize. And then we will have n lambda 40 Q-core 1, the same QWin. And then in the second run, I keep the same number of points, but then I will put 20, Q-core 20, and then I keep the QWin. Maybe I forgot to say it. The code will distribute half the points between Q-core and half the points between QWin. So then in this case, what we are saying is that 20 points should be distributed in this equivalent Doppler unit range. And in this case, 20 points will be distributed in this equivalent wavelength range. So then again, I save the files, then I restore them. So if you uncomment these lines, then you can do it by yourself. And then I make this plot. So then this is case 3 versus case 4. Okay. So in order to allow you to better visualize the differences, now I'm putting a vertical line where you have a spectral point. Okay. So we have the blue and the black profiles, but also the vertical lines. The blue ones are corresponding to the case 3, where we have Q-core 1. And then black is a case 4 where Q-core was 20. Okay, so then what you are seeing is that in the case of 1, you have 20 points in this region that I would say that is too narrow, because it's basically just the bottom of the line core. And then you can see that as we move outside the Q-core range, this exponentially move. So then here are closer, and then they start to get separate. And then if we compare with the Q-core 20, the spectral sampling is linear in all this range, but this range is very big. So then the distance between these black points is constant, but is too big, mainly for this region. So then, for example, in this case, as we have a linear, so then between this and this and this one is the same, but the blue one that had a lot of points in this region, it has less density, in fact, in the WIN. So it's not evenly distributed, neither of these cases. So then what I had here is that in the case 3, we have a too narrow range, and in the case of 4, it's too wide. So again, there's no strict rule, but I would say that something between 2 or maybe between 5 and 10, I would say that is something reasonable. But always, I recommend you to just change it, do a synthesis, read the profile, make a plot with the spectral points, as I said, and just double check that is a reasonable value. Okay, and now let's do the same, but with QWin. So now case 5, we have 80 points and 80 points. And then Q-core is fixed to 5. And then in one case, QWin is 80, and in another case is 400. Okay, so again, what I do is I run, so I change the atom with this value, I make a run, and I stop, I save the profile, then I change the atom again, I make a run, and then I save the profile. Okay, then I restore the save of the profiles, and then I make this plot. That is case 5 versus case 6. Okay, so in this case, again, we have vertical lines for each spectral point, but I made the plot, the wavelength range, much larger to allow you to see that with the same QWin, it seems that it's okay. So we have blue and dark lines very well distributed around the line core. But then when the Q wing is 80, in case 5, you can see that things were okay until this point. And then suddenly you have a flat and there's no points in between. And the same here. So then with just 80 for this specific line, you are not reaching the wings. And then it means that you are not with a good configuration. In the case of 400, then you are reaching the wings, and in fact you are going too far. So again, this is something that you can quickly check. My advice is similar as before, so something in between 100 and 200 is reasonable, but it depends on the line. So lines like Hans said, magnesium 2 or calcium 2 that are very broad, usually you may need to go farther than 200, definitely. But maybe with calcium 2, 8542, around 150 is probably reasonable. Okay, so then I hope this helped to understand more or less the different parts. And then I would say that for me, this is a reasonable configuration. So 70 points, Q core 5 and Q win 150. So I run again for this example. And then I plot this case 7. And then you can see that in this case, it looks as more or less what we want. So the core, remember that it was the line core, steep part, and then the knees. This is covered with a high density of spectral points. And then even if they are exponentially distributed, they still are enough to have a smooth shape, and they are reaching far enough to cover the continuum. Okay, so I would say that this is a good start. Of course, you can change it, but my advice is just do one computation, check the profile, and then of course you can then run multiple pixels of a simulation or something like that. But at least be sure that you have an idea of how the configuration works for the spectral lines of interest. Okay, so and I think that's all for this part. Yes, so then let me go to the summary. Yes, so as a homework, just try to run the test. Maybe you can try to reproduce case 1, case 2, or just make a case of something that you think. So maybe you can put n lambda like 1000 or 20 and try to check how it works. It's important to try to understand Q core and Q win, or at least to know which values you should play with. So I think it's not reasonable to think on Q core 50, and it's also not reasonable to think on Q win 1. So just try to have an idea, and then maybe the fine adjustments will require a few minutes. But as soon as you have one configuration, you will have it in principle forever. So then it's worth it to just double check. And then try to also read. So when we read the ray.input, so here, when we do this, this ray.input, it contains the full spectrum. So then you already have loaded the calcium H and K lines and the other lines. So if you have time, it's good to try to check if, for example, the current configuration that I think was default, it's enough, or if you would like to play a bit until having a bit better. And the reason is that next week we will focus on these two lines, and we will check the difference between PRD and CRD for them and for the calcium line. So it's good if you already try to do the same I did today for these two lines. And then let me go back. And yes, so next class, it will be simple. So today I was thinking if I added some of these, and I said, no, let's keep it short today, and then next week the same. So the idea is that next week it will be very simple. We will just check what happens if you compute the calcium line in LTE and in non-LTE. We will get a feeling of iterations, and we will compare that with the atlas. So this should be relatively fast, but it's something that is also good that you should know how to do it. And then the second one, that is what happens if you, instead of using void, you use PRD in the atom, and when do you need to do that? I think the best answer is you should try for the lines that you are interested on and check that CRD works, or if not, you should use PRD. And then sorry, there was a chat, sorry. I was reading the chat. So, and then we will check it with calcium H and K that they are lines that are traditionally sensitive to PRD, and you will see that it has a strong impact, and it's a requirement, in fact, for really making sense of the profile shape. Okay, so then I think that's all. Next class will be again Friday, but I think I wanted to just focus on this. So I think I went slow, but please, if you have any question, just let me know, and I can go back to the atom file or to the script, because we have yeah, it was only 45 minutes today, so we'll have time enough for questions. Okay, this sounds like no question. So then next week we will finish covering the things related with the atoms of input and how we compute the lines. And after that, we will move probably to the LTE lines, how to provide them to RH and how they are computed and what things are required to synthesize them. Okay, so then if there are no questions, then see you next week.
Yeah. Thank you.
Okay.
Thank you.
Okay.
See you.
Bye.
Bye-bye.
Bye.
Bye-bye.
Thank you.
Bye.
Thank you. Bye.
Bye.
Bye.